The last topic we'll look at in this lesson is looking at how you can decide whether or not a particular system is at equilibrium, and knowing that if it's not at equilibrium, we'll be able to decide which way it needs to shift in order to reach equilibrium. We're going to use something called the reaction quotient in order to help us to do that. If you think back to the first activity that you did with the nitrogen dioxide and the N2O4, you had one person who was the forward reaction, you had one person who was the reverse reaction, and then you had somebody else who was the checker. And that person asked you to stop, and they did a count, and they verified whether or not you were at equilibrium. They did so by checking if you reached that magic ratio of 6 and 10. Essentially, that's what we're going to be doing in this case. We're going to be looking at the equilibrium at a moment in time, looking at what we have in the system, and deciding if we're at equilibrium. When we talk about the reaction quotient Q, essentially what it's going to be is the exact same expression as the equilibrium constant expression. It's essentially whenever the system is not at equilibrium, we call it Q instead of calling it K. Or if we're not sure, we call it Q. So let's look at this example here. We've got the Kc for this reaction is 0.145. And it says, which way would the reaction proceed initially if the following amounts are put into a 1 liter flask? We've got the amount of BrCl, Br2, and Cl2. In order to decide if the system's at equilibrium, what we need to do is plug into the reaction quotient, which, as I said, is called Q, and it's the same expression as the equilibrium constant expression. So in this case, it's Br2 times Cl2 over the concentration of BrCl squared. Now, it's always really important to pay particular attention to the units that you're given. So you're given the moles for each of these, and you're told that it's in a 1 liter flask. Okay? Because it's a 1 liter flask, the concentrations are the same, but if it wasn't a 1 liter flask, you would need to deal with that appropriately. In this case, the concentration of Br2 is 0.02. So what we're going to do is plug in the values that were given for each of the concentrations. You need to be very careful and make sure that you square the 0.05 because that's consistent with the equilibrium expression. When we compute this, we find that we get 0.16. By comparing this value to the equilibrium constant, which is 0.145, we can see that they're not the same. If this were a system at equilibrium, the value for the Q would be 0.145. Because at equilibrium, the ratio of reactants and products is equal to 0.145. In this case, we know that it's not at equilibrium because the value for Q is not equal to K. Okay, so Q is not equal to K. You can see above here that when Q is larger than K, we're going to need to proceed in the reverse direction. Okay, but let's look at the logic of that. Okay, let's think about the Q in terms of it being the products over the reactants. If it's the products over the reactants and it's too large, we can see that it's the denominator of this expression that needs to increase in order to make the value 0.16 lower to become 0.145. So in this case, the reaction, okay, and RxN is a short form for reaction, must proceed in the reverse direction. So connecting this to that very first activity that you did, the looker or the watcher may have said, okay, we need more products. The forward reaction, you need to go faster. Or we need more reactants. The reverse reaction, you need to go faster. Okay, so it's the same kind of thing that's going to happen here. The BRCL, we need more of it. So the reaction is going to proceed to the left in order to achieve that, okay, or in the reverse. Okay. What I'd like you to do at this point is to actually try this question. Okay. I'll give you the reaction. It's CH2O is in equilibrium with CO and H2. So it's asking you which direction the reaction needs to go initially. You've got some of each of the reactants and products. You're going to need to determine Q and make a decision about the direction of the equilibrium. Be careful in this case, because in this case, it's a 10-liter flask instead of a 1-liter flask. So you will need to determine the concentration. The same kind of calculations could be done if we were given the partial pressures of the substances and the Kp value.